Yes, good morning. I am going to explain what is a superconductor. Do you know what is the working mechanism of magnetotrain? Magnetically levitated trains, also called bullet train, designed by Japan scientists. Can you guess how much of magnetic field present inside MRI scanner, which is used in hospital? And these are all applications of superconductor. And what is a superconductor? We know that from basic standard, materials classified into three categories based on their electrical properties: conductors, semiconductors, insulators. Every material offers finite amount of resistance, even conductor also. Insulator offers huge amount of resistance. The resistance of semiconductor intermediate between conductor and semiconductor. Superconductor resistance. What about superconductor resistance? Superconductor, as the name itself indicates, its conductivity is more because of zero resistance. It offers zero resistance. But this property, this topic, superconductor, is a subject of low temperature. That means superconductor acts as a superconductor with zero resistance only at low temperature. Now, research is going across the globe to find out a superconductor at room temperature. Why? Because if superconductor is available at room temperature, almost no need to pay current bill. Why? The reason is very simple. Conductor offers finite amount of resistance, every conductor. Superconductor resistance is zero at low temperature, as I mentioned earlier. If the resistance is zero, the current flows in a wire for many years. For many years. Once you inject a current in the superconducting wire, it flows continuously for many years. That is what we call persistent current. If the question is how many years, I can't say 2 years, 3 years, 4 years. And many textbooks mention this as 10 power 5 years. Many years. The problem with superconductor material, superconductor, is nowadays we don't have superconductor at room temperature 300 kelvins. If it is existed, superconductor at room temperature, there are so many advantages with such material superconductors. Maglev train, do you know what is the function of maglev train? Average speed 500 km per hour, invented by Japan scientists. So there is no physical contact between trains and tracks. You may ask a question, how this is possible? This is possible with high power magnets, electromagnets, using superconducting wires. Like that in MRI scanning also, the huge magnetic field is used in MRI scanning. That is also possible with superconducting wires. Okay, now let us discuss about what is the origin for this superconductor and superconducting state. What is superconducting state? Just now I mentioned. Superconducting state means a state with zero resistance. But the resistance of superconductor is zero only at low temperature. The first scientist, Camerly Honus, who discovered superconductivity in the material mercury. At the time, he measured what happens to the resistance of liquid metal like mercury. We know that metals offer finite resistance at room temperature 300 kelvins. Now you just imagine what happens if the resistance is increased or decreased. For example, if the resistance of metal decreases, then resistance also decreases. If temperature increases, resistance also increases in the case of metal. Now what he observed, Camerlingonus, in the year 1911, he observed what he observed in mercury. Now he measured resistance at different temperature, and as temperature decreases, suddenly at one particular temperature, that is what we called critical temperature or transition temperature. It is a characteristic of the material. It changes from material to material. For example, we take mercury. It has Tc. It is different from other superconducting material. Now, below this Tc, what happens at this Tc particularly? Resistance drops to 0. But actually, what we are expecting in the case of metal, as we decrease resistance of metals, resistance goes on decreasing and decreasing, and still it has a finite amount of resistance even at 0 Kelvin, low temperature 0 Kelvin. But in the case of superconductor, resistance drops to 0. This particular temperature is called critical temperature. That means up to this region, the material is in superconducting state. That means its resistance is 0. And if the temperature is above Tc, it is in normal state. What is normal state? Normal state means a state with resistance. So that means a superconductor has zero resistance. Is it sufficient? The condition is sufficient for a material to become a superconductor? No. Because in addition to this zero resistance state, the material has another property proved by Meissner. What Meissner stated that when the material is in superconducting state, it should be perfect diamagnetic material. Perfect diamagnetic material. That means so far what we discussed, a superconductor means zero resistance. A superconductor means zero resistance at low temperature, that is below Tc, critical temperature. In the case of mercury, it's around 4.2 kelvins. Practically, it is impossible to achieve such a low temperature in our physics lab. Almost it is close to 0 kelvins. That means you just take superconductor Hg and you want to change that superconductor normal metal, liquid metal, mercury into a superconductor. What we need? We need a cooling system to produce such a low to create such a low temperature on a physics lab, 4.2 kelvins. It is impossible. Practically, it is not impossible. 4.2 kelvins, what is it? How can you achieve for such a low temperature? 4.2 kelvins corresponds to liquid helium temperature. Liquid helium temperature. This 4.2 liquid helium. Helium is a gas, and liquid helium temperature. It changes to liquid at 4.2 kelvins. 4.2 kelvins is a low temperature. It is a coolant agent. Liquid helium is the coolant agent. Now this zero resistance state, this zero resistance is not sufficient, and one more condition is required, that is proved by Meissner. What he stated? Yes, diamagnetism, perfect diamagnetism. Now let us discuss about what happens when the superconductor is placed in an external magnetic field. External magnetic field. Okay. Now you take a superconductor. Initially it is a normal, it is in the normal state. That means T temperature should be greater than Tc. Just now I mentioned, if the temperature is below Tc, it is in superconducting state. Now it is a normal state. Now as we decrease the temperature until we get T less than Tc. Now this is in superconducting state and this is normal state. Normal state and superconducting state. Now we placed this superconductor in external magnetic field. Yes, this diagram indicates that when the material is in normal state and which is placed in external magnetic field, it allows magnetic lines of force to pass through the material. Now we can measure B inside the material. It is not equal to 0. Magnetic induction. Whenever there is magnetic lines of force, we can measure magnetic induction. But in the case of superconductor, it is equal to 0 as magnetic lines of force are repelled by the material. Repelled by the material. That means in the normal state it allows magnetic lines of force. In the superconducting state, it is repelled, magnetic lines of force are repelled by the material. Or the magnetic induction inside the material, because no line is passing through the material, hence the magnetic induction B is equal to 0. I can prove that if the magnetic induction inside the material is 0, then this material is a perfect diamagnetic material. We know the basic properties of paramagnetic material, diamagnetic material, ferromagnetic material and different magnetic materials from basic standard, from 8th standard. Now we have a connection between three parameters. B is equal to mu naught into H plus M. And this is the relation between three parameters: magnetic induction, and this is magnetic field intensity, and this is intensity of magnetization. Just now what I said, B is equal to 0 inside the superconductor. Now you put B is equal to 0 inside in this formula, then you get mu naught into H plus M. As A into B is equal to 0, either A is equal to 0 or B is equal to 0, but this has permeability has a value 4 pi into 10 power minus 7. It cannot be 0, and but H plus M becomes 0. That means H is equal to minus M. R M by H is equal to minus 1. What is this M by H? This M by H is defined as chi, magnetic susceptibility. Magnetic susceptibility. Chi is equal to minus 1. It clearly shows that the material is a perfect diamagnetic material when the material is in superconducting state. Yes, so hence for a material to be a superconductor, two properties. One is zero magnetism, zero resistance 0, and perfect diamagnetism, perfect diamagnetic material. So these are the two properties. Okay, now so far what we discussed, how to change a normal metal into a superconductor. Very easy, by decreasing the temperature until we reach Tc, then it changes to superconducting state. Now I provide a superconductor. And what is the method to destroy that superconducting state? How many methods are there? Yes, what are the methods to destroy a superconducting state? I am going to explain the destruction of superconducting state. Okay, listen. Now I am going to explain about critical magnetic field. What is critical magnetic field? Critical magnetic field. What is critical magnetic field? Yes, and this is superconductor. Initially, I have a superconductor, that is T less than Tc, because below Tc the material is in superconducting state. Yes, if I placed this superconductor in external magnetic field, is there any line? Is there any magnetic lines of force inside the material? No, because just now I explained, according to Meissner effect, it is a perfect diamagnetic material. That means the flux is repelled by the material. Flux repulsion. Keeping temperature constant, I am going to change strength of the magnetic field. Applied magnetic field. What happens? Is there an effect on the superconductor? Yes, definitely. Now I am going to increase the external magnetic field. External magnetic. I am going to increase external magnetic field, keeping temperature constant, T less than Tc. What scientists discovered? As we increase the external applied magnetic field, there is a chance of passing magnetic lines of force through the material. Once it passes through the material, then the state is not a superconducting state, the state is normal state. Here the question is about at what field, what is the strength of the field at which this line, the magnetic lines of force, passing through the material and the material changes to normal state. Keeping T constant, temperature constant, I am changing magnetic field, I am increasing the magnetic field. Slowly, there is a chance of passing magnetic lines of force through the material. Once it passes through the magnetic material, once it passes through the material, then material changes to normal state. Now here the question is, at what field? What is the strength of the field? That strength of the field is called critical magnetic field. Critical magnetic field. So we have seen what is Tc. Tc is critical temperature. It is not critical magnetic field. Critical temperature changes normal state into superconducting state. Critical magnetic field changes superconducting state into normal state. Critical magnetic field. And what is the value of critical magnetic field at this transition temperature? Here is the question. This is very important topic. And what is the critical magnetic field value at critical temperature? Can you guess the value of critical magnetic field at critical temperature? Very easy. Very easy. Because at the critical magnetic field, at the critical temperature, already the material is in which state? It is in superconducting state. When the material is in superconducting state,